We started section 311 last time on the hyperbolic functions. So what we did last time was we defined the hyperbolic functions and then learned the formulas for the derivatives of those 6 functions. So now we're going to finish this section, and next we're going to look at the inverse hyperbolic functions and formulas for the derivatives of those. Now that we've defined the 6 hyperbolic functions, we can talk about whether they have inverses or not. So if you remember the theory about inverse functions from pre-calculus, a function has to be one-to-one in order to even have an inverse function. So it turns out that hyperbolic sine and hyperbolic tangent are one-to-one. We never looked at the graphs of these functions, but if you looked at them, they would pass the horizontal line test, meaning they're one-to-one. So they're fine. We know they have inverses. However, the hyperbolic cosine is not one-to-one. But if you restrict its domain to just 0 and bigger, that part of the graph is one-to-one. So when we consider the inverse hyperbolic cosine, it's assuming we've restricted the domain to going from 0 to infinity. So now that we know these 3 functions have inverses, we can define those inverse functions in the way that we usually do. So take hyperbolic sine, the inverse. To write what it means in terms of plain hyperbolic sine, you just interchange the input and output, right? So if for the inverse of the hyperbolic sine, if the input is x and the output is y, when we rewrite its meaning in terms of hyperbolic sine, we switch that so the input is y, the output is x. And we do the same with the other functions here. Now we're going to look at the derivatives of there are 6 inverse hyperbolic functions. So we'll start by finding the derivative of the inverse of hyperbolic sine. So we start by letting y equal the function we're trying to take the derivative of, and then just apply the meaning of this function that we saw earlier. If you interchange the input and output, this is equivalent to saying hyperbolic sine of y equals x. Now remember, we're trying to find dy dx, right? Because dy dx represents the derivative of the function we're asked to find the derivative of. So trying to find dy dx, but this equation is not solved for y, which means we need to use implicit differentiation. So we're going to take the derivative of both sides of this equation here with respect to x. Now on the left side, that's mixed variables, a function of y, but we're taking the derivative with respect to x. So we start with the outer function, which is the hyperbolic sine, and we take its derivative. So we learned that earlier in this section. Derivative of hyperbolic sine is hyperbolic cosine. Keep the input the same, right? It was y here, so input should stay as y here. Then we have to multiply by the derivative of the inside part. The inside part is y as a function of x, so that derivative is dy dx. And then the right side is easy. Derivative with respect to x of x, same variable, so it's just 1. Then we would solve this for dy dx by dividing both sides by hyperbolic cosine of y, and that gets us to this point. But we don't want to stop here because we want to express this derivative in terms of x, not y. So we need to make a substitution in the denominator to rewrite that in terms of x. So to do that, we're going to use this identity that we saw earlier in the section. Right, this was one of the identities for the hyperbolic functions. So then take that and solve it for hyperbolic cosine, so then we could plug it in here. So to solve this for hyperbolic cosine, we would first add the hyperbolic sine squared to the right, and then you take the square root of both sides. and that would give you this. Now technically you have plus or minus in front of the square root, because when you take the square root of both sides you have to put plus minus. But we know that hyperbolic cosine is always 0 or bigger because of the restricted domain that always happens. And so we know this has to be the plus square root. So now we have a substitution we can make in the denominator. We replace it here. And then the final substitution comes from right up here. We know that the hyperbolic sine of y is equal to x. So we're replacing that with x and noticing that it's squared. The denominator is now the square root of 1 plus x squared. So we just derived this formula for the derivative of inverse hyperbolic sine. Here's a table showing the derivatives of all 6 of these inverse hyperbolic functions. Notice here the derivative of inverse hyperbolic sine is the formula we just derived. So you could use similar methods to find all these other derivatives. We're not going to go through all those. I'll just present these formulas to you. And again, you do not need to memorize these. Just if you're given these formulas, be able to use them. And so we'll do some practice with that over the next couple slides. In this example, we're going to compute some derivatives. And I've put the formulas that we just saw on the top right so we can reference those. So the first one, we've got inverse hyperbolic cosine of 3x squared minus 5x plus 1. So clearly a chain rule problem, because the x has been replaced with some other expression. So we start with the derivative of the outer function, which is the inverse hyperbolic cosine. So looking at the formula on the top right, we can see what that is. So dy dx equals, so that formula we've got 1 over the square root. Now here we see that x squared, but remember we're not using x, we're using the inside part in place of x. So you can see the inside part in our function is what's in the parentheses. So I'm going to take that expression in place of the x, and since the x is squared, this expression is now squared. And then it's still under the square root. After that we have a minus 1. Okay, so that's the first half of the chain rule. We've done derivative of the outer function. Next we have to multiply by the derivative of the inside part. And that's a pretty straightforward derivative, 6x minus 5. And it would probably look best just to put that in the numerator. So I can remove the 1 that I wrote there and put in its place 6x minus 5. And you could simplify if you wanted, but I don't think it's really necessary here. Okay, so just applying the chain rule along with one of these new formulas we learned. Let's go to the second one. So here our derivative we can call f prime of t. So you see the inverse hyperbolic tangent, but it's the inside part, right, to another function, which is the cubing function. So this is another chain rule problem, but this time the hyperbolic part is the inside part. The outer function here is a power function, right? U cubed. So we start with the power rule. You always start with the derivative of the outer function. So we bring the 3 down in front, keep the inside part the same, reduce the power by 1, so now it's squared. That's the derivative of the outer function. Now we multiply by the derivative of the inner function. And that is just, it's not a chain rule problem or anything for that derivative. It's just straight from this formula. The only difference is we're using t in place of x. So it will just be 1 over 1 minus t squared. And then if you wanted to make this look a little nicer, we could write it as 3 over 1 minus t squared, and then multiplied by this inverse hyperbolic tangent squared. And that's it. Got a couple more functions here. This one, number 3, is inverse hyperbolic secant of t over 2. So our derivative notation here could be dz dt. Now let's look at the, again, this is a chain rule problem because we have something else other than plain t plugged in. So our outer function is the inverse hyperbolic secant. So if you look at the formula over to the right, we see negative and then a fraction, numerator 1. Now in the denominator, x appears twice. Both of those x's get replaced with our inside part, which in this case is t over 2. So we have a t over 2 in front, and then square root 1 minus t over 2, which is then squared. Okay, so that's the derivative of the outer function. Now we multiply by the derivative of the inside part. So the derivative of t over 2, right, we could view that as 1/2 times t, and the derivative of a constant times t is just that constant. So we multiply by 1/2, which you could put in the numerator. So I'm going to get rid of this 1 and replace it with 1/2. That's the first, oh no, that's all of the chain rule, right? That's it. We did the derivative of the outer function times the derivative of the inner function. Now simplifying, notice if we multiply by 2 over 2, that will cancel out the 2 and the 2 that are in those two places. So that would definitely make it look nicer. So negative, and then our numerator is now 1, and then in the denominator, we just have t, we got rid of the over 2, and then the rest could stay the same. Okay, and that finishes number 3. Going to number 4, this one, we do have a chain rule at some point, right, because there's 8x instead of a plain x. But notice the bigger picture is the product rule. We have a product of 2 functions of x, so we need to start with the product rule. So our derivative will be dy dx. We start with first times derivative of the second. Now the derivative of that inverse hyperbolic sign, this is where we're going to use the chain rule. So the outer function is inverse hyperbolic sign. Looking at the formula up at the top for that derivative is 1 over the square root 1 plus x squared, but we replace that x with our inside part, which is 8x, and then that has to be squared. That's the derivative of the outer function. Now we multiply by the derivative of the inside part, which is 8. So I'm just going to put that in the numerator. I got rid of the 1, replace it with 8. Now we're part way through the product rule. First times derivative of the second. Now we're ready to move on to plus second times derivative of the first, which would be 4x cubed. Now we'll make this look a little bit better. On the first term, it might look nice to keep the denominator. I guess if you wanted to, you could rewrite 8x in parentheses squared as 64x squared. Now in the numerator, I would just move the x to the 4th up with the 8. So 8x to the 4th. Now on the second term, it always looks better if you have something multiplied at the end of a function like this. It's better to put that in the front. It's just easier to read that way. So 4x cubed times this inverse hyperbolic sign of 8x. Okay, so in these examples we saw how to incorporate these new derivative formulas into bigger problems where we're using a combination of other formulas with those. Now I want to spend some time reviewing for your midterm exam, which will be tomorrow. So make sure you see the announcement in Moodle for more details on the technicalities of the midterm, including your proctor. So you should already have your proctor in place and have that schedule planned with them. And then see the details also about how the exam will be sent back and forth. So the midterm will cover everything we've done up to today. And so here I've just listed out exactly what sections we've covered. It's basically most of chapters 2 and 3 with a few sections that we skipped. The problems will be similar to homework and quiz problems. So because of that, I think the best strategy for studying is to review the old homework and quizzes, and not just to read solutions that you've already done, but try to work them from scratch again to make sure you can do that, because that's what you have to do on the exam, right? You don't have to just read solutions and understand them. You need to be able to create the solutions yourself from scratch. Just like on quizzes, make sure you show your work, and again, this is to your advantage because I can give you partial credit this way. You may use a calculator on the midterm, but nothing else, right? No book, notes, etc. You can't have your phone with you. I will provide you with a formula sheet, so you don't need to bring I've posted it in Moodle so you can see exactly what's on it, but you don't need to bring your own copy. I'll provide that to your proctor and they'll give you a copy. But make sure you look over that formula sheet ahead of time so you'll know what's on there, and you can make sure to memorize any formulas that you'll need that are not on there. Before we get into the specific points of the review, I think it's really helpful to get a broad overview of everything we've covered and see how it fits together, all the pieces fit together. So we started with chapter 2, and the topics here were limits and derivatives. So the major themes, first we presented the tangent problem. This is the motivating problem for all of differential calculus. And I think we all are familiar with what this problem is, right? If you have a graph of a function and you pick a point on that curve, sketch the tangent line at that point, and the problem here is how to find the slope of that tangent line. So as we made a strategy for how to solve this problem, we realized we needed a concept of a limit. So the next thing we did was formalize that concept of what a limit is. And then, based on that view of a limit, we practiced how to calculate limits of functions. So we learned some methods that could be used to help evaluate the limits. Next, we defined the concept of continuity. And the reason why that's put here right after learning about limits is the definition uses a limit. So we learned how to do certain problems about evaluating whether a function's continuous or not at a point using this limit definition of continuity. Next, we moved back to our tangent problem. Now that we had this concept of a limit, we can solve the problem, and the formula we arrived at that solves the problem is so widely used that we gave it a special name, and that's the derivative. So we defined the derivative to be a particular limit, right? It was a limit of a difference quotient. And we now had the solution to the tangent problem with this new derivative, which is defined using a limit. So then we practiced calculating some derivatives using this limit definition. Later on, we'll learn shortcuts So we stopped using that limit definition after this chapter because we basically went and found shortcuts to make it a lot easier to get to the same result, but without having to use the limit definition. But that's all in chapter 3. And then the next thing we did was how to interpret a derivative as a rate of change. So anytime you have a functional relationship, the rate of change is important, and it's the rate at which the dependent variable changes with respect to the independent variable. So the derivative can be interpreted in context of the meaning of the variables in your function. So then we move to chapter 3, and the main theme of this chapter was finding these differentiation rules, so learning them and how to use them. And these rules help us a lot because they give us a way to calculate derivatives without having to use the limit definition. Right, we did a few examples in chapter 2 using the limit definition to calculate derivatives and saw that it's very difficult. In most cases could get really complicated. So these differentiation rules are going to make finding derivatives a lot easier. So here's a list of the rules we learned. Right? First we learned if you're taking the derivative of a sum or difference, how to handle that just by going term by term and taking the derivative of each term individually. Then we learned the power rule. So this is for the derivative of your variable raised to a constant power. And by the way, those two rules together enable us to take the derivative of any polynomial very quickly. Then we move to the product and quotient rules. So the key thing here is if you're taking the derivative of either a product or quotient of two functions of x, you cannot take the derivative term by term. You have to use the formulas for these two rules to handle those situations. Next we learn the chain rule, which tells us how to take the derivative of composite functions where you have an inside part and an outside part. Next we move to implicit differentiation. So this is a case where your formula is given not in the normal function form, so it's not solved for y in other words. So we learned a method here where you could still find dy dx even though the original equation is not solved for y, not in the normal function form. Next we learned some more differentiation rules for the derivatives of logarithmic functions. And then we also learned some more formulas for the derivatives of the inverse trig functions. I guess I didn't list earlier, but earlier we learned formulas for the regular trig functions. So I'll just add it to the list. Inverse trig functions and just the plain trig functions. Although we learned those earlier in the chapter. And then in the very last section, we learned the formulas for the derivatives of the hyperbolic functions and the inverse hyperbolic functions. Before that last section, we inserted some other topics that were not differentiation rules, but some other things we're interested in related to derivatives. And one is related rates problems. So that was, for example, blowing up the balloon was one of the examples we did. The radius is changing at the same time the volume is changing. So the rates at which those two things are changing were related. And then we also did a section on linear approximations and differentials. So this was another use of derivatives for approximating something. One thing you want to be prepared for on any test is to be able to recognize a type of problem so that you'll know what strategy to use, what methods we've learned in class that can be applied to that type of problem. So here I'm going to just go through a basic list of the different types of problems we've seen that you're responsible for, and to think about what strategy we use for each type. Right? Because on the test you won't be told what method to use. You need to know what method applies to which type of problem. So let's start with the velocity problem. So we talked about two types of velocity if you have an object moving in a straight line. Average velocity and instantaneous velocity. So average velocity is always over an interval, whereas instantaneous velocity is talking about at a single instant in time. No, it's no longer over an interval. So when we first encountered this problem, we could only estimate the instantaneous velocity. But you can calculate average velocity, right? There was a formula for that. It's if the interval goes from A to B, the average velocity would be the ending position minus the beginning position divided by ending time minus beginning time. So it's the elapsed distance over the elapsed time. Now, in order to find instantaneous velocity, at this point we're just estimating. What we did was created a table where you chose your interval to get smaller and smaller down towards the single instant in time that you're interested in. And you calculated the average velocity over each of those intervals. And then you looked at your table and you tried to tell whether that average velocity is getting closer and closer to some number. And if it is, then you could guess that the number that those are approaching is your instantaneous velocity. Okay, another type of problem is to estimate the value of a limit. So it wasn't until later that we learned how to actually calculate for sure what a limit is. At this point, we were doing practice with estimating limits, and these problems were good exercise because they really help you understand better what a limit means. So here, in this type of problem, you would be given a formula for your function, and you'd be asked to evaluate, the limit of that function as x approached some fixed number we'll call a. And to estimate it, you would use a table again. You would have an x, we're not using intervals this time like we were in the velocity problem. You would just create an x column and an f of x column, just like plotting points. And then for your x values, you would choose numbers that get progressively closer to a, whatever number that happens to be. So if a were 1, you might choose x to be 0, and then 0.5, 0.9, 0.99, and so on. And you might also choose them approaching a from the right, getting closer and closer to a, or whatever that number is. And then calculate all the f of x values that go with your x's, and then look at the table and see if the f of x's seem to be getting closer and closer to some number. If they appear that they are approaching some number, then you would guess that number is the value of this limit. Now a similar problem, estimate the value of a limit or a one-sided limit based on a graph rather than a formula. Right? So if you were given just a picture of f of x but not the formula, just look at that picture to help evaluate a limit. Next, find vertical asymptotes using limits, right? So not all functions have vertical asymptotes. But if you suspect that it does and you want to prove that it does, you can show that using a limit. This usually involves first guessing where the vertical asymptote is. And a good starting point for that is to look at values of x that make the denominator 0. It's very possible your graph would have a vertical asymptote at one of those points. So if you guess it's at x equals some number a, then you need to look at the limit as x approaches a of your function, and then try to evaluate that limit, or estimate it if you can't evaluate it. And if you can show that limit is either plus or minus infinity, that means you have a vertical asymptote at a. Then we started learning methods to help us evaluate limits without having to guess, and those are the limit laws. So things like limit of a sum or difference, or limit of a product, limit of a quotient. Basically, we saw you could split the limit up to the individual terms in any of those, sums, difference, products, quotients, as long as all the individual limits exist. And then along with that, we learned how to use direct substitution in some cases. Right, so if you're looking at limit as x approaches a of some function, sometimes it's okay just to replace all the x's with a. So just take your function and plug in a for all the x's. You can't always do this, right? We saw this only works in some cases. So if you have a piecewise function, you never want to use this method because it may not work. But if it's not a piecewise function, it works in most cases, and the only cases where it generally doesn't work is if plugging in a results in a 0 in the denominator. In that case, the limit might still exist. It may or may not exist. You have to investigate it further in those cases and try some other method to determine the limit. So we'll continue with more types of problems. So there are some examples of limits where you are asked to evaluate where the squeeze theorem could be used to evaluate those limits. And most likely the problem would ask you to use the squeeze theorem. So if you take the function if you consider the function that you're asked to find the limit of, you have to find two other functions. We'll call them f and g, that satisfy a few things. First of all, your function has to be between f and g, and the limits of f and g have to be the same. If you can find these two functions, f and g, that satisfy that, then that means the limit of your function has to be the same as the limits of f and g. Okay, another type of problem, finding points where a function is discontinuous. So you need to use the limit definition of continuity. So make sure you know that definition. And what it says is limit as x approaches a of f of x equals f of a. If that's true at the point a, then f is continuous at a. So if you suspect it's discontinuous at some number, say a equals 3, then you need to prove that this definition fails for a equals 3, and that would prove you have a discontinuity there. Now a related problem is to find the intervals where a function is continuous. And notice here it says intervals rather than points. So an interval just means, or continuous over an interval means it's continuous at every single point in that interval. So here you have to think more broadly. You have to find all the points where it's discontinuous. So all points of discontinuity, and then it would be continuous everywhere else. So then create your intervals so they omit all of those points of discontinuity. Okay, next, using the intermediate value theorem to prove the existence of roots. So here the problem might be posed. You have some expression in terms of x, we'll just call it f of x equal to 0, and you want to prove there are solutions, and solutions would be called roots. So you need to either, if they give you an interval, that makes it easier, but if they don't give you an interval, you have to choose an interval from some number a to some number b, and you want, when you look at the corresponding y values, f of a and f of b, you want one of them to be positive and the other negative. So f of a and f of b have to have opposite signs. That's sort of the starting point for this. If you can do that, and another really important thing is you have to check to make sure that f is continuous over the interval you chose. Because one of the hypotheses for this theorem is that your function is continuous. So if you can check that and make sure and find an interval where all this works, then you can say by the intermediate value theorem there must be a root somewhere between a and b. So this theorem, it doesn't find the root, it just proves existence. Then we had more evaluating limits, but these are limits at infinity. So that's referring to limits as x approaches either plus or minus infinity rather than x approaching a finite number. Okay, so we review the techniques for how we evaluate these limits. You obviously can't use direct substitution because you can't plug in infinity for x. There was one specific technique that can be used if the function f is rational. Meaning a polynomial divided by a polynomial. The technique here is you find the highest power of x in the denominator and you divide top and bottom by that expression, right? So if the denominator has x cubed, and that's the highest power of x anywhere in between numerator and denominator, then you would divide the top and bottom by x cubed and then simplify, and then you should be able to take the limit from there. So I'm not going to write all that. I just want to mention if f is rational, we have that specific technique, and that only works for these limits where x is going to plus or minus infinity. Okay, so then another type of problem deals with tangent lines. So if you're given a function and you're asked about a tangent line at a particular point, we know that you use the derivative to find the slope. So you would take f prime, and then you first find f prime of x, and then you plug a in for x, where a is the point, the x coordinate, where the tangent occurs. And then to write the equation of the tangent line, you first have to find the slope using what we just described, and then use the point slope form is usually the easiest way to do these. Use the point slope form of a line, plug in the slope that you found using the derivative, and then plug in the x and y coordinates from the point where it's tangent. Another type of problem is finding instantaneous velocity, or more generally, instantaneous rate of change on something. So we've already made the connection that instantaneous velocity is found by taking the derivative of the position function, which we usually call s of t for the position function. instantaneous rate of change, then whatever it is you're finding the rate of change of, you need to have a function for that. And the instantaneous rate of change would be the derivative of that function. And then those are usually word problems, so make sure you check units and make sure you're doing all the analysis that the question might ask. So this next one covers a huge number of topics that we discussed. Differentiate a function. Almost all of Chapter 3 was learning rules for differentiating various types of functions. So a key part of this is being able to look at a function and determine which rules you need to use. Often you might need to use multiple rules to complete the derivative. Next, we had problems where you were given the graph of a function and not a formula, but based on the graph, be able to sketch what its derivative would look like. Okay, so you had to look at tangent lines at various points on the given graph and try to estimate the slope of those tangent lines in order to graph what the derivative would look like. Determine where a function is or is not differentiable. It's helpful if you could graph the function because it's easier to see this. So a graph can help. If they give you a formula, you might want to sketch a graph. And there were 3 situations that you could see on a graph that would tell you there's a there'd be a point where it's not differentiable. So one of those is it's not differentiable if you have a corner or a cusp, or if there's a discontinuity, so either a hole or a jump, or a vertical asymptote, that kind of thing. And then the third was if you have a vertical tangent. Okay, so if you see any of those situations in your graph, whatever the x-coordinate is associated with those features, it would not be differentiable at that x-coordinate. And then we had finding higher derivatives, so like a second derivative or a third derivative and so on. So it just means that you continually keep taking the derivative. So start with f, that would be given to you. Find f prime as usual. And then if you take the derivative of f prime, you now have f double prime. And you can keep going for higher derivatives. And then using implicit differentiation. So you would only use this technique if the given function is not solved for y. Okay, so review the techniques here for how to do implicit differentiation. So we also have related rates problems. So these would be word problems, and you won't have a title, they won't present the word, this is a related rates problem. But you'll recognize it because they'll give you one rate, and they ask you to find another rate. Okay, so you'll want to review all the steps here, but just a key thing to remember is usually you have to find, so you need to label the rates, which means you need to introduce variables. And then you have to find an equation that's like your starting point. So you need to find an equation that relates the 2 variables that are involved. And then you need to use implicit differentiation on that equation. Okay, and then there's some more to it, but those are some of the key steps involved in that method. Another problem, find the linear approximation for a function at a point. If you want, this is the function we called L of x, and if you want, you can memorize the formula for this, right? The formula is f of a plus f prime of a multiplied by x minus a. If you don't want to memorize, and again, a here is the x-coordinate where it's of the point of interest. But if you don't want to memorize the formula, just realize this is the tangent line at x value a, and you can just use the methods we've learned earlier for finding a tangent line and solve it for y, and that's this function. And then you have problems where you not only find the linear approximation, but then you use it to approximate something, right? So we did some examples where we asked you to approximate things like the square root of 3.98. So you might define f of x to be the square root of x, and then find the linear approximation to that function at a nearby point to 3.98, which would likely be 4, right? So find the tangent line at x value 4, and then plug 3.98 into that function. And then related to that were differentials. So if you're asked to find a differential, make sure you know the formula. So the differential dy is defined to be f prime of x times dx. So finding this is very simple. You just calculate f prime of x using rules of derivatives and plug it in here. And that's it. Sometimes there'll be more to it. They might ask you to plug in a specific value for x and dx. So you'd first calculate dy like I just described, and then you'd plug in the given numbers. And then another use for the differential is estimating error. So we did an example here where your tool for measuring something has a known maximum error. The example we did was like measuring a sphere by measuring the radius of a sphere, and there's some maximum error in that measurement. And then you calculate the volume of the sphere using the volume formula, and we want to estimate the maximum error in calculating the volume based on the known maximum error for measuring the radius. So we're going to go through several examples just to get some practice on various types of problems. In this first example, we're given a graph of a function f of x, and I'm going to ask you to evaluate several limits based on this graph. So let's start with the limit as x approaches, let's say, -3 of f of x. So what we would do is first find -3, so that's right here, right, because these are units of 1. And looking at where the graph is, we want to consider what happens as we approach -3 from either side. So let's say we are approaching from the right side. We'd be following along this part of the curve, and it would approach this dot right here. And as we approach -3 from the left side, notice it comes to the same dot. So let's investigate where that dot is. It's right about here. And let's look over to see what the y-coordinate is. It looks like it's -1.5. And since it was the same on both the left and the right sides, then the limit exists and equals that common y value, -1.5. Okay, let's do another one. Let's do the limit as x approaches -2 with this plus here of f of x. So remember that superscript plus means from the right. So -2 is right here, and we're approaching -2 from the right, right? That doesn't mean, the plus does not mean towards the right, it means from the right. So that means we'd be following along this part of the curve, and notice it's going up towards positive infinity. So the limit would be infinity. So that's an example of an infinite limit, when the limit value is infinity. It's also a type of not existing, right? We would say this limit doesn't exist, but by saying infinity, it's a specific way that it doesn't exist. Now let's do similar, except x approaches 2 or -2 from the left. Right, the minus sign means from the left. So approaching this, here's -2, approaching from the left means we're following along this curve, and it's going down forever towards negative infinity. Okay, let's do another one. Let's do the, oh, and by the way, those two results together tells us the regular limit as x approaches -2 does not exist, right? Because the left and right, we can't even say infinity, right? Because it's plus on infinity on one direction, negative infinity on the other. Okay, now let's go to the limit as x approaches 0 from the right. So let's look at our picture. At x value 0, we're here. We're approaching 0 from the right, which means we're coming along this part of the curve, approaching this point that has y value -3. So even though the function is undefined at 0, this limit did exist as x approached 0 from the right, and that was equal to -3. And then the limit as x approaches 0 from the left, so this time we're approaching 0 from this side. It means we're coming along this curve, and it approaches this point, which has y coordinate 0. So that limit would be 0. And then those two one-sided limits tells us if we were asked to find the regular limit at 0, it would not exist because the left and right limits are different. And then let's do one more. Limit as, or maybe two more, and limit as x approaches infinity. So that means we're letting x get infinitely large off to the right. And if you follow along the curve, notice the y values are leveling off at a height, at a y coordinate of -1. Okay, so that limit is -1. Now let's do the limit as x approaches negative infinity. So now we're going off to the left infinitely far, which means we'd be following this curve, and notice it's not leveling off, the y values are going downward infinitely. So that limit would be negative infinity. So those last two are referred to as limits at infinity because x was going to plus or minus infinity. So this is an example of evaluating limits based on a graph rather than a formula. Here's an example of evaluating some limits. There are so many different situations you can encounter in evaluating limits. We're not going to have time to practice all of them, but I picked 3 representatives of different types. So the first thing we almost always try is direct substitution. And as long as it's not a piecewise function, you can at least attempt this. If you get something that's defined when you direct substitute, then that's most likely your limit unless you have some strange situation. So in this first one, if we plug in 2 for x, we get sine of 2 pi over 4. And if you simplify the 2 pi over 4, which becomes pi over 2, use what you know about the unit circle, sine of pi over 2 equals 1. And remember, as long as your function here is continuous, we know we can use direct substitution. And the sine function, of course, is continuous. So we're done with that one. Now the second one, if we tried direct substitution, notice the denominator will be 0. But we do not conclude that the limit doesn't exist, right? It's still possible the limit exists. We have to work further. So one thing we often try in this situation is factoring and see if there are any common factors that cancel. So notice here the denominator could factor to x minus 1 times x plus 2. And there is a common factor that cancels between the numerator and denominator. When we cancel those, we get 1 over x plus 2. Now we try direct substitution again, and this time we're fine because we get 3 in the denominator. So remember, this is a rational function, and you're allowed to use direct substitution as long as the denominator is not 0, and that worked here. The next one, notice x is approaching infinity. So we can't, of course, you can't use direct substitution in those. And because this is rational, there was a specific technique that works, but only if x is going to infinity and you have a rational function. What we do is we take the highest power of x in the denominator, which in this case is x squared, and we divide top and bottom by x squared. So I'm going to multiply top and bottom by 1 over x squared. Now when you're simplifying limits, make sure you keep writing the limit sign until you actually take the limit. Right now we're just simplifying the function inside the limit. So in the numerator, when I divide 3x by x squared, you can cancel out a common factor of x, and that leaves 3 over x. And then we have minus 1 times 1 over x squared. In the denominator, the first term, 4x squared, when we divide it by x squared, becomes 4. On the next term, 5 over x, when you cancel out a common factor of x. And then the third term is plus 2 over x squared. Now any term that is a constant over x to some power, I'm going to circle all those. Think about what happens to those terms as x goes to infinity, right? Those fractions would go towards 0. So if we go ahead now and we take the limit, everything in the numerator went to 0, right? 0 minus 0 is 0. And in the denominator we have 4 plus 0 for the limit. So we end up with 0 over 4, which is 0. So that is the limit on this one. This example, we're given a formula for a function. You can see it's a piecewise function, and we're asked to find all points of discontinuity. Now if you look at the 3 individual functions, polynomial, constant, which is polynomial, a third is polynomial, each piece by itself is continuous because polynomials are continuous everywhere. But with piecewise functions, any x value where you jump from one formula to another has the potential to be discontinuous at that point. And you can see it's at x coordinate 1 where you have to, if you're on either side of 1 or if you're at 1, it determines the formula. So there's a possible discontinuity at x coordinate 1, but we need to determine if it actually is continuous or not there. So we have to justify this using the definition of continuity. So the definition, we would say f is continuous at 1 if, and this is the definition, so you'll need to make sure you know this definition, limit as x approaches 1 of f of x equals f evaluated at 1. Okay, and I put 1 in there because that's the point that we suspect we may have a problem. So remember, this definition implies 3 things. First of all, the limit that is expressed there has to exist. Second, f of 1 has to exist. And third, they both exist and they're equal to each other. If any one of those fails, that proves it's discontinuous at x-coordinate 1. So the easiest one to check is what I called number 2. Let's look at that one first. Does f of 1 exist? Well, let's look at our formula. Since we're wanting to plug in 1 for x, we need to use the second formula, and that means the output is 3. So f of 1 equals 3, so it does exist. So we didn't have a problem there. So let's look at the limit next, which I called number 1. Limit as x approaches 1. Now, because of having a different formula on each side of 1, that suggests we need to consider one-sided limits in order to determine the regular limit. So let's start with the right-sided limit. So if for a right-sided limit, that means we're approaching 1 from the right, which means x is greater than 1. So if x is greater than 1, we're in this category, and we can replace f of x with the formula x squared plus 1. Since that's a polynomial, we can always evaluate those limits using direct substitution. So we get 1 plus 1, which is 2. Now let's do the left-sided limit. Okay, so when x is approaching 1 from the left, that means x is less than 1, which means we use the top formula. So we replace f of x with 2 minus 3x. Another polynomial, so we evaluate with direct substitution. 2 minus 3 gives us negative 1. So the one-sided limits, they both existed, but notice they're not equal. That tells us the regular limit as x approaches 1 does not exist. And that means this definition fails, right, because one piece of it didn't exist. Since the definition of being continuous at 1 fails, that means f is discontinuous at x-coordinate 1. And there's no reason to suspect a discontinuity anywhere else, right? Because 1 was the only coordinate where we had to jump from one formula to another, and the individual pieces are all continuous. There will definitely be questions on the exam like this, asking you to differentiate functions, because we spent a long time learning the various rules for that. So let's start with the first one. We're going to have to use multiple rules to differentiate this, so you have to be able to see what's the first rule you should start with. And the big picture is we have a quotient. Within that, we'll have to apply different rules to the numerator and denominator, but we have to start with the big picture and use the quotient rule first. Okay, so here f prime of x equals, in our denominator, we take the original denominator and square the whole thing. Now in the numerator, we start with bottom times derivative of the top. Now the top has a square root, so it might help if you rewrite the function and write the numerator as 3x plus 1 to the 1/2 power. That always makes taking derivatives of square roots easier. Okay, so back to derivative of the top. That's a chain rule problem because it's not just plain x to the 1/2, it's some other expression to the 1/2. So the outer function is the 1/2 power function. So we need the power rule first. So we bring the 1/2 down in front, reduce the power by 1. 1/2 minus 1 is negative 1/2 for the new power. That's the derivative of the outer function. Now we multiply by the derivative of the inside function. The derivative of 3x plus 1 is 3. Okay, so that finishes the first term in the numerator. That's bottom times derivative of the top. Now we have minus top times derivative of the bottom. So the derivative of x squared minus 2 is 2x minus 0. And then from here we could do some simplification. I'm not going to be too picky about how you simplify things, but make sure when you do simplify that you don't make mistakes, right? You don't want to take something you did correct in calculus and then change it to something that's incorrect. So in the first term in the numerator, we could put the 3 halves in front, right? The 1/2 times 3. And then we have in the numerator, we've got that factor x squared minus 2. And then the term with the negative 1/2 power, we could put that in the denominator as a positive 1/2 power, and you could translate the 1/2 power back to a square root. And then in the second term, I might just put the 2x in front of the square root term. And there's more you could do with that, right? Because you might not like that double fraction, right? Fraction within the numerator, but I don't want to take our time now to work on that part of it. Let's just go on to the next problem. So an inverse secant. So this is one of the formulas that will be provided to you on your formula sheet, the derivative of inverse secant. So make sure you know what's on the formula sheet so you'll know when you see a problem like this, you'll know, oh, I know that formula's on my sheet and I can look at it and use it here. So here's what it says on the formula sheet. Derivative of inverse secant of x equals 1 over x times the square root of x squared minus 1. So the version we have is going to be a chain rule problem, because instead of just a single letter it plugged in, we have some other expression, which is in this case t cubed. So the notation here would be dy dt for our derivative. The outer function is the inverse secant function. So first we apply that formula over to the right. But wherever we see an x, we need to replace it with the inside part, which is t cubed. So in the denominator we have t cubed in place of that first x. And then under the square root, where we have x squared, that will become t cubed squared. And then it's still followed by minus 1. That's the derivative of the outer function. Now we multiply by the derivative of the inside part, which is 3t squared. So we could just put that in the numerator. So I'll erase the 1 and put in its place 3t squared. And there's a couple things we could do to make this look nicer. We could divide top and bottom by t squared. So now the numerator is t. And in the denominator, t cubed divided by t squared is t. And then under the square root, where we have t cubed squared, we multiply exponents there, so that would be t to the 6th minus 1. And there, that looks a lot nicer. So like I said, there are many other situations you might encounter when you're asked to differentiate functions, so you'll want to make sure you review all the rules we covered in Chapter 3. Here we're given a graph of a function f, no formula, but just a graph, and we want to sketch what f prime would look like. So remember, what you want to look for are picking some points on the graph of f, sketching the tangent line, and estimating the slope of the tangent line. And a good place to start is to locate the points where the tangent is horizontal. So I notice a few of these. Right, one is right here, horizontal tangent, another one here, and a third one. So whatever those x-coordinates are, we know the slope of the tangent is 0 at those x-coordinates. So when we graph f prime, we want to have value 0 at those 3 locations. Okay, so this one was at x-coordinate -2. and the slope is 0. So over here at x-coordinate -2, we plot a y value of 0. This one occurred at an x value 0. Again, the slope is 0. And at x-coordinate 3, slope 0. Then, next thing is to start looking at these subintervals created by the dots I just made. So for example, to the left of this red dot, let's see what's happening. At any point here, if you envision the tangent line, it would be a positive slope. Right? That's true on all of these in this subinterval. So the slopes here are positive. So that tells me when I graph f prime over this subinterval to the left of this red dot, the y values will all be negative. Before I actually sketch that, let me just make a note here. So negative. Now between the next two red dots, if you pick any points here and sketch a tangent line, you'll see it has a negative slope. Right, there are different slopes at each point, but they're all negative. Oh, and sorry, I said that wrong. The first one had positive slopes, so I don't know why I wrote negative there. Right, if you look at the lines all above that, they all had positive slopes. And in this next subinterval, they all have negative slopes. Now when we get to the third subinterval between these two dots, pick points in here, sketch the tangent. They all have positive slopes again. Okay, so that means positive y values down here. And then the final subinterval to the right of this last red dot, all the tangent lines here have negative slope. So we're back to having negative y values. So now envision sketching where we start out positive, which means above the x-axis. We hit this red dot and then it becomes negative. We have to arch back to get to this red dot, and then we switch over to being positive. We have to arc back to hit this red dot, and then when we hit it, we switch back to being negative. So let's fill in a curve that does that. So here it's positive, hits the red dot, becomes negative, pass through the next red dot, becomes positive again, pass through the next red dot, and becomes negative. Now this is just an estimate of f prime. We haven't spent enough time figuring out how high these arcs go. Right? We're just getting a general idea with this type of graph. We're given an equation and then asked to find dy dx. If this were a function, right, f of x equals, or y equals some expression with x's in it, we could just straightforwardly apply any of the differentiation rules we've learned that are appropriate. But this one is not in that type of form, right? It's not solved for y. If we could solve it for y, we could put it in that form, and that would make it easier to find the derivative. But this one would be really impossible to solve for y, mainly because we've got one y in the exponent and another y that's not in the exponent. There's no way to solve for y in that situation. So we have to use implicit differentiation in this case, which means the first step is to take the derivative with respect to x on both sides. And you can split that derivative up across a sum. So on the left we have derivative of the first term minus derivative of the second term. And we do the same thing on the right. All these derivatives need to be with respect to x. Now let's go through these one at a time. The first derivative we have is derivative of 3x with respect to x. Notice the variables are the same. That makes this a straightforward derivative. It would just be 3. Now on the next one we've got mixed variables. So we have to remember we're actually using the chain rule on a problem like this. So first we take the derivative of e to the 2y with respect to y, which is in and of itself a chain rule problem because it's not just a single letter in the exponent. So the outer function is the exponential e to a power, and the derivative there is itself, keeping the inside part as it is. And then we have to multiply by the derivative of the inside part. So the derivative of 2y with respect to y is 2. Now this was really a chain rule within a chain rule, right? Because what we just wrote was the derivative of e to the 2y with respect to y, but we were asked to find it with respect to x. So what we found was the derivative of the outer function. The inner function is just y as a function of x. So now multiplying by the derivative of the inside part is just dy dx. Now let's go to the right side. The next derivative is completely in terms of x, so it's just a straightforward derivative using the power rule. We get 2x. And then the last one has mixed variables. So we start with taking the derivative of y squared with respect to y, which is 2y, and then multiply by the dy dx factor, which is, again, the derivative of the inside part. Okay, that completes the first step. The next step is to use algebra to solve for dy dx. And so what we always want to do first is to get all the terms that have dy dx in them on the left and all the other terms on the right. So I'm going to keep this term on the left because it has a dy dx. And then I'm going to move this term over to the left by adding to both sides. So it will become on the left side plus 2y dy dx. And on the right, I'm keeping the 2x, but I'm moving over this 3 from the left over to the right by subtracting 3 from both sides. And once we do that, you can then combine all the dy dx's that are on the left by factoring it out. So we get dy dx factored out. And then what's left inside, I think I'm going to put this term first because it's positive. 2y is left here. And then minus 2e to the 2y left on the second term. We could have factored out the 2 if we wanted, but either way is fine. And then we'll keep the right side the same. And then the next step, to get dy dx by itself, we just divide both sides by what's in the brackets. So on the right, our numerator is 2x minus 3. And then we divide by what's in the brackets. Okay, and that's the first thing we were asked, was to find dy dx. The next question is find all the points on the graph with a horizontal tangent. So we have to make sure we know what our strategy here. So a horizontal tangent means it has slope 0. So we would just set the dy dx, which is the slope, equal to 0. But the only way a fraction can equal 0 is if the numerator is 0. So it's faster if you just straightforwardly set the numerator equal to 0. And then you can solve that for x. You get 3/2. So we found the x-coordinate for points that would have a horizontal tangent. If you wanted to actually give an ordered pair, you'd have to solve for the y that goes with it, which means plugging 3/2 back in for x in these two places, and then trying to solve for y. But the problem is we still have this issue of one y in the exponent and one y not in the exponent, so we can't solve that by hand. So in this case, we'll have to be satisfied with just giving the x-coordinate. So any point on the graph that has x-coordinate 3/2 would have a horizontal tangent. Now I'll just mention, if the problem asked to find vertical tangents, we know that means the slope would be infinity, and the way that would happen with the slope expression as a fraction like this is if the denominator were 0, that would result in the fraction being infinity. So if it asked for a vertical tangent, you would set the denominator equal to 0. We're told the radius of a circle is increasing at a rate of 3 centimeters per minute, and then we're asked to find the rate that the area is increasing when the radius is 8 centimeters. So first you need to recognize this as being a related rates problem. Notice they gave us one rate, the rate at which the radius is increasing, and they asked us to find another rate, right, the rate that the area is increasing, and those two rates are clearly related to each other. So we need to introduce variables so we can start writing mathematical expressions about what's going on. So the rate that they gave us is for the radius, so we definitely need a variable for the radius. So let's use r for the radius, and notice distances here are measured in centimeters, so that'll be the units for radius. Also, they're asking us to find the rate for the area, so we need a variable for area. Use capital A. And if distance is in centimeters, then area would be in square centimeters. And both of those are changing over time. Notice the rate has centimeters per minute, so we can tell that time is a variable here also, and units in minutes. Now let's write out the given rate. So the rate for the radius, how fast the radius is changing over time. So that would be dr dt, and that is 3 centimeters per minute. And then the rate we want to find is for how fast the area is changing over time, so dA dt. So you want to make sure to clearly label your two rates, the given one and the one you have to find, and write them both as derivatives. Now we need an equation that relates the two variables in our rates, right? We have radius and area. Without the derivatives, the two variables are r and a. We need an equation that relates those two variables. So this is one where we should be able to all know this, right? The area of a circle, pi r squared. I'm not going to expect you to know formulas for all kinds of figures, you know, cylinders and various geometric figures, area, volume and surface area formulas. If it's something that's not as well known as, say, a circle, I would just provide the formula to you. But you should know, you know, area of a circle, perimeter of a circle, area of a square or rectangle, that type of thing. Okay, so now that we have our equation, we use implicit differentiation. And since both a and r are functions of t, we want to take the derivative with respect to t on both sides. So starting with the derivative of area with respect to t, those are mixed variables, right? We have an a here, a t here. So we first take the derivative of a with respect to a, which is just 1, and then we multiply it by the derivative of the inside part, which is dA dt. This one, you don't even really have to think that way. You can just see this is dA dt, right? Now on this one, mixed variables again, and r inside, and taking the derivative with respect to t. So first we take the derivative with respect to r, so carry along the pi because it's constant, bring the 2 down in front, reduce the power from 2 down to 1. That's the derivative of the outer part. Now the inner function is r as a function of t, so we have to multiply by dr dt. Now, look, we can plug in the given information and solve it for, you can do it in either order. Why don't we solve it first for the one we're trying to find, which is dA dt. But notice it's already solved for dA dt, right? Because we can drop off this 1. So that we don't have to move anything around. That part's done. Now we're going to sub in the given information. So we know dr dt is 3. And then we're also told at what instant we're trying to find the rate. And that's when r is equal to 8. Okay, so that's what we're going to sub in here. So now on the left we have dA dt. On the right we have 2 pi times 8. And then plug in for dr dt. That's supposed to be a 3, not a 0. And simplifying, we get 48 pi. And make sure you put units on it. Notice the derivative here is, so it should be units of area over units of time. So square centimeters over minutes. Okay, and so this example illustrates the basic strategy for related rates problems. So we're out of time for today. So clearly we didn't cover examples of all the different types of problems you're responsible for. I just picked a few areas of common types of problems. So you want to make sure that you go back and review everything. So some study suggestions. First of all, make sure you complete the review problems that I posted in Moodle. The answers are included so you can see if you got to the right answer. If you didn't get to the right answer on some problems and you have questions about how to solve those, feel free to contact me to discuss your questions. Also, many of the exam problems will be similar, not exactly the same, but similar to old quiz problems. So I definitely suggest you review those and don't just read the solutions that either you wrote or that I posted in the solutions to the quizzes. I suggest you rework them from scratch before you look at what the correct solution is. Right, you want to get that, you want to spend most of your study time practicing solving problems, not just reading and understanding solutions, but actually writing them yourself. And you want to get to the point where you can do that without having to use any notes or resources. Also, rework selected homework problems. You won't have time to go back and rework all of the problems probably. So pick the areas where you had a little bit of trouble, especially when you were reworking quizzes, if you had trouble with a particular type of problem. Find those types of problems in the homework and focus your time on reworking some of those problems. And then if needed, generate even more problems of a particular type beyond the quiz and the homework. So you can see my suggestions here are really practicing solving problems. Reading to understand concepts can help, and I suggest you do that. But I think you should really focus most of your study time on practicing solving problems.